So I'd like to thank Professor Zohreh Davoudi for joining us today to talk about towards quantum simulations of quantum field theory. So thank you for joining us. Dr. Davoudi received a PhD from the University of Washington, Seattle, and joined MIT after that in their Center for Theoretical Physics as a postdoc. And she has been an assistant professor of physics at the University of Maryland College Park since 2017. She studies strongly interacting systems such as hadrons and nuclei using analytical and computational methods, including effective field theories, lattice, quantum chromodynamics, quantum simulation, quantum computing. And today we'll hear about a lot of this. So thank you very much for joining us. And please take it away. I will stop sharing. Oh, one quick announcement, just to next month's talk, I will plug, if I can forward my slides here, myself. I will talk about some of our work on noise characterization, mitigation, and so on. All right, let me stop sharing and let you go.
All right, thanks very much. Let me start sharing my slides. Okay, great. Thanks a lot for the invitation. It's great pleasure to be here and talk about this exciting topic that has kind of emerged in the past few years, maybe past decade, has gained a lot of momentum. And that's the topic of how we can use quantum simulation and quantum computing technologies to simulate quantum field theories, and in particular, quantum field theories of interest in a standard model of particle physics. I'm Zohreh Davoudi, as was introduced, and my background is particularly in nuclear physics and lattice gauge theories, with a special interest in using computational methods to simulate from first principle interactions in nature and properties of matter, including hadrons and nuclei, and strong interacting matter in general. So I'm going to give you some sort of a flavor of what this program is about and sort of showcase some of the things that people have done to accomplish some of the early goals of this program. And of course, this is going to be a very long program, and we're hoping that with the advent of quantum simulation technologies, we eventually reach where we are today and beyond with regard to the simulations using the classical techniques. So we would like to actually accomplish this now with quantum technologies and do more. And I want to motivate this because I think for this crowd, maybe it's not, you're not very familiar with what type of physics problems are the ones that we would like to study, and what kind of sort of precision we would like to achieve in describing qualitatively or quantitatively the properties of these nuclear physics systems. So very short motivation from my perspective for leveraging these quantum technologies is the following. We have done quite a lot actually with classical computing techniques to study, as I said, from first principles, properties of matter. And I don't want to go through all those progress. And in fact, much of what I've done so far in my physics career is to actually contribute to this program of classical computational techniques for studying this strongly interacting nuclear physics systems. But we have reached really the era when we understand what the limitations are and what kind of problems we cannot hope for our classical techniques to be able to address. So let me give you a flavor of what these kind of problems are. In particular, whenever we are dealing with a large quantum many-body system, of course, and this could be nuclear isotopes, dense matter, and so on, we are going to deal with very large Hilbert space, of course, and some of the classical techniques that we're using, and in particular Monte Carlo sampling techniques, would break down. So for example, I'm showing a picture of what is called a phase diagram of quantum chromodynamics, or QCD, which is the theory of a strong force in nature. And I'm showing this picture, but in fact, we don't have quite a good idea of what different phases of matter is when they are strongly interacting. And these are just theoretical conjecture in this picture that are either experimentally being explored or there are some models and hypotheses for what they should look like. But unfortunately, from the standpoint of theoretical calculations, we cannot perform calculations that are precise enough to actually go beyond sort of this axis of this plot, which is the temperature. So as soon as you increase the number of the nucleons in the systems or introduce a high chemical potential, then there is a range of interesting exotic phenomena that could occur, but our current computational technologies would not allow us to explore them. And in particular, for example, we don't know what the equation of a state of, for example, the dense nuclear matter would look like, such as those in the core of the nuclear stars, in the interior of neutron stars, and so on. And as I said, this is simply a limitation of the method at the moment. The way we do these classical computations are based on the path integral formulation of quantum mechanics, but in Euclidean spacetime, simply because we want to have a well-defined weight for our Monte Carlo sampling. And as a result, introducing any kind of chemical potential to the picture would bring a very severe sign problem. And that requires exponential improvement in the computational resources in order to get any signal out of these computations. Another set of questions that we haven't been able to really address with our classical computational techniques just yet are related to anything real time. As I just mentioned, our techniques so far have been based on quantum Monte Carlo in Euclidean spacetime, where the time is imaginary. However, if you're interested in a range of dynamical quantities, for example, what happens as two heavy ions would collide in experiments, or what happens after the Big Bang. We know the fundamental interactions. We know the standard model is responsible for what happens in the visible sector of the universe, and as a result, in this kind of very exotic collisions. But as a function of time, we have not been able to track the process since the collision and understand exactly how the matter would come to an equilibrium, thermalizes, expands, freezes out, and forms the hadrons in our collider, in our detectors in these collider experiments. Everything so far is sort of phenomenological approach based on what we've seen in experiments and what we expect from the theory, but there hasn't been sort of a first principle simulation that starts from initiating these collisions and then tracking out the state of the matter after these exotic conditions. This would be very hard for the current techniques. And this is just one example. There's a wealth of dynamical quantities, such as response functions, transport properties, and a sort of dynamical matter distribution functions, if you're familiar with them, what is the structure of a hadron or a nucleon from the perspective of a standard model, or in particular, anything non-equilibrium physics of QCD. These are the type of questions that unfortunately we haven't been able to really explore, again, because our methods are really not real time. We are doing path integral in imaginary time, and kind of naturally, these kind of problems would require to do a Hamiltonian approach or Hamiltonian simulation approach to the problem, in which you think about the time evolution operator. Of course, we all know that formulating these problems in the language of Hamiltonian Hilbert space is going to be very difficult, and with the classical resources, very, very costly. So again, if we want to do path integral in real time, we are going to have the maximal amount of sign problem that you get in these Monte Carlo simulations. So this has been very prohibitive so far in terms of the classical techniques. So we are not short of the important problems that we would like to explore eventually with the new computing technologies. And that's why we're hoping that with the advance and progress in the quantum simulation and computing technologies, we kind of port these problems and reformulate them in a language of Hamiltonian simulations, and maybe learn about these kind of quantities that we are interested in. Maybe firstly, qualitatively, even that would be good enough, and then eventually with precision. Okay, so quantum simulation in nuclear physics let me just kind of define the overall picture very schematically, what we mean by quantum simulation in nuclear physics. Okay, so what we actually mean is that we would like to leverage a quantum system that can be controlled, whether in a digital or an analog fashion, to study another quantum system that is more elusive, in this case, these nuclear physics systems, either experimentally or computationally, as I said, either in an analog fashion or a digital fashion. All right, so what does that mean? If you look at this picture, which is sort of very schematic, what we are saying is that down here, we are starting with a theory of quarks and gluons of the standard model. They interact strongly through the strong interactions or QCD, but also other interactions. They form an atomic a nucleon, and then eventually an atomic nucleus. But of course, we know that the atomic nucleus would be the core of an atom itself. The atoms would make the molecules would make the matter, in particular quantum matter. And you can also eventually think about microscopic objects or astrophysical objects, such as neutron stars and so on. Everything kind of arises from bottom up from this picture of the quarks and gluons. But what we are hoping to achieve is that we know that studying from first principle, this part of the diagram would be very difficult. And currently we have been very limited with our classical computational resources. But we are saying that maybe we should use these systems that are intrinsically completely different in terms of interactions and scales and so on, with the systems that we're interested to study in QCD, in nuclear physics, kind of leverage these kind of systems, atoms, molecules, materials, whether in a digital fashion or a more natural analog fashion, to learn something about these underlying interactions and the subatomic particle physics, right? And maybe eventually we can even attack problems of the size of astrophysical objects. That would be the hope. So this is really kind of the very schematic of what this program would be. And of course, this is kind of the right time to start thinking about these problems. I don't have to say this to this crowd, but we know that there are a range of exciting quantum simulator and quantum computing technologies out there, whether at universities or national labs or at the private companies, that are really pushing the limits of what's possible in terms of hardware technology for really the next phase or the next generation of these devices. Of course, they are not there. They're not at the level of sort of reliability and scalability that is required to address even a small instance of the problems that we have in mind. But eventually the goal is that hopefully within the next decade or a few decades, we will have these devices. And it might sound sort of very far-fetched, right? I mean, I'm talking about problems that are really huge in terms of, and I'll tell you a little bit about that aspect later on. And we're hoping to sort of all of a sudden use this quantum technology to solve them, and we don't even have this hardware. That's a good question, but I should tell you that from the background that I'm coming from, this lattice gauge theory program, we were kind of, I wasn't there, of course, maybe 40, 50 years ago. The community were at the same point, because at the time, people started to say, well, maybe we should start computing these non-perturbative strong interacting systems from QCD, from a standard model. But they didn't have the big computers at the time, the big classical computers at the time. At the moment, all they could do were very sort of small lattices or small instances of these problems. But they were very patient, and they started to really develop what is required to transform this kind of continuum quantum field theory program to a program that is more computational and numerical oriented. And along the way, this hardware technology came along, and these supercomputers got better and better, and the algorithms got better and better. And we are at the point that we can actually simulate an atomic nucleus from a standard model. This is a huge achievement. Nobody would have thought about this 40 years ago when the program started. So we are in a very similar situation, I think, with quantum technologies. You can argue maybe not quite. We don't know whether we will have this super quantum computers at some point in the future, or even quantum computers. But let's be patient and let's see what we can do at the moment, assuming that we will reach that point. All right. So that's really the goal. That's sort of ideology in our community, that what we should do at this point. So now the question is, well, we have the quantum chemistry. Of course, there's been a lot of developments, whether in terms of algorithms and hardware implementations and so on, in trying to achieve what is not possible classically in quantum chemistry problems. And you might ask, are there similarities that you can borrow from the quantum chemistry community and then apply here to this kind of nuclear physics problems? And the answer is yes, of course. A lot of these algorithms and developments are very useful. And in fact, they can be ported to our program as well. But I want to emphasize that there are also major, major differences. And that's why developments are necessary. And we have to come up with new ways and new ideas, new algorithms to attack this rather different problem, although we can still build upon what's out there for other fields, including condensed matter and quantum chemistry problems. Let me give you some idea of what these differences would be. So let's say that, forget about quarks and gluons, these building blocks of a standard model. Let's say that we've already given a nucleon, which is already made of quarks and gluons, but I don't want to go that fine grained and think about a standard model degrees of freedom. Let's say just I already have the nucleon. And these nucleons would come together through strong interactions, form an atomic nucleus, and they interact and they make reactions and so on, which would be of interest to us, right? So let's say that we have the nucleons and we want to start from nuclear Hamiltonian and then solve the quantum simulation problem for whatever reason that we're interested in, whatever particular problem that we would like to look at. So what are the differences here with the quantum chemistry Hamiltonian? Well, now the Hamiltonian of these nucleon-nucleon interactions is actually more complex, and itself might not even be known with arbitrary accuracy. In fact, we have to do a lot of experiments at different scales and come up with various ways to parameterize them to really have an accurate description of the Hamiltonian itself. The Hamiltonian has short range, intermediate range, and long range interactions associated with that. So it's not just like nearest neighbor or local. Not only we have two-body interactions, we can have three and multi-body interactions in these nuclear systems. This is something that you don't see in quantum chemistry. But also there are bosons like pions and other hadrons that can become dynamical in these problems. They can actually mediate the nuclear force in these nuclear Hamiltonians. So the problem is not just fermionic nucleons, but it could be a mixture of fermions and bosons and so on. So these are kind of some differences. I would argue that the differences are even more significant if you start from a standard model degrees of freedom. Let's not take for granted the fact that like these nucleons exist and they interact with each other. Let's zoom in a little bit and say, we're interested to systematically start from quark and gluon degrees of freedom of the standard model, build a nucleon, then build a nucleus, and so on. Very sort of bottom-up first principle approach that we are doing in the lattice gauge theory program nowadays with the classical resources. How if we want to do this also with the quantum resources? Then the differences with the quantum chemistry type problems would be even more significant. Why is that? Because now we are dealing with the quantum field theory descriptions and not just a non-relativistic description of this the fermionic system, but also these systems are not only fermionic, they are bosonic and fermionic, they are dynamical, they're coupled. And these theories of a standard model, they exhibit not only the global symmetries, but also very important local gauge symmetries. And more importantly, they are relativistic. So particle number is not conserved. And the vacuum state of the strongly interacting theory could be completely non-trivial. So these are the features that you only see these sort of relativistic quantum mechanical systems then you don't have to deal with this non-relativistic quantum chemistry systems. And that's why the developments have to happen quite a lot in this program before we can claim that we have the right suitable algorithms for simulating gauge field theories of a standard model, for example, on a quantum computer. And I'm gonna mostly focus on this aspect as opposed to the other aspect, because kind of my background is already in this lattice gauge theory program, the program of starting from a standard model interactions and building the visible matter out of it in this computational approach. So are there any questions for me? I can't see the chat, so if the host please would let me know if there are questions or comments at this point, I'll take them.
There's nothing in the chat, but I am monitoring it if folks want to ask there. I did have one question actually, since you stopped. So you mentioned all of these long range interactions. Most Hamiltonian simulation algorithms that I'm familiar with assume some sparse structure to the Hamiltonian. So this, can you comment on the complexity challenges of simulating, I guess, how filled up is the Hamiltonian when you discretize it and try and simulate it?
Yeah, so the interactions are longer. So, I mean, interactions are long range, but in the end of the day, they are not infinite range. In fact, the range of interactions is controlled by the Compton wavelengths of the lightest hadron in nature, which is the pion. And so it actually dives off. It's a Yukawa potential, as opposed to, for example, Coulomb potential in quantum chemistry that you're dealing with. But I mean, in the end of the day, if you had a simulator that was like fermionic, right, not a qubit-based quantum computer, and you had like this mapping of the fermions to fermions, then your interactions are actually just the two-body interactions. And all you had to deal with was to sort of engineer this kind of variable range interactions between these fermions, which would have been whether difficult or easy depending on the hardware that you pick, right? If you now map this fermionic system to a qubit architecture, then you have to deal with all sorts of problems that arise when you map the fermions in 3 dimensions to a qubit architecture. So the fact that the interactions are long range, it doesn't really change the fact that you have to deal with non-localities when you map the fermions to the qubit architecture. I think these are kind of two different things, but they kind of arise in the same problem, right? They emerge in the same problem in the same way. You have a long-range interaction, but it's kind of the two-body interactions between the fermions. But as soon as you map it to your qubit architecture, depending on the mapping that you pick, you might have to deal with very non-local sort of high weight spin chains, right, to simulate. So my answer to this is that there hasn't been enough studies of what is the complexity of mapping this problem. There are some work that is being done on this direction, but that would be kind of no different than what's being done already sort of in the Hubbard model, Fermi-Hubbard model, or other problems, because it's really very similar in the nuclear problem. You have the fermions that are interacting either locally or non-locally, and you have to map them to the qubit architecture with some sort of mapping.
Thank you.
No problem. All right, so let me continue. So as I said, I want to focus on this program of quantum simulation of quantum field theories. And I argue that this is, and sort of the schematically, again, this is a sort of the picture that we have in mind. We have a controlled quantum system, whether in an analog or digital fashion, like the trapped ion systems, and so on. And we're hoping to use sort of this really kind of simple system, right? If you think about it, it's kind of a simple system with simple interactions. And we're hoping to build very complicated interactions of a standard model, in this case, quantum chromodynamics or strong interaction physics, out of this simple controlled quantum system, whether in a digital way or in an analog way. And the question is that, is it possible? Maybe your system is too complex, as we just mentioned, then we cannot do this efficiently with this sort of simple quantum hardware. But kind of that's not the, the vision that we have. And we're hoping that step by step, we can build the requirements to actually complete this mapping. But we have to start from simpler models. We cannot just start from the strong interaction theory, which is QCD, which has a lot of challenging features to it that I will talk about. But we start from simpler models and understand how to do these kind of mappings, and then we go from there. And as a result, this program really is a multi-pronged program. It requires not only theory developments to really understand how this mapping works to a completely different system, right? But also like algorithmic developments. So sort of from the pure problem of defining this is the Hamiltonian, then what are the best efficient algorithms for near-term and far-term applications on the quantum hardware. And we would like to also do the implementation and benchmarking along the way. Otherwise, we are going to be blind to the technologies that are available or being progressing. And maybe at some point, we can also impact the progress in the hardware side, because then that this community would get aware of the type of Hamiltonians and physics we're interested in, and would start to kind of have a specialized hardware for these kind of problems, if that's going to be the future. And in fact, from classical computing side, there are examples of this in developments of parallel and supercomputing technologies. Lattice QCD or lattice gauge theory program have actually impacted the course of developments of these different generations of this hardware. So we can imagine that because this is a really complicated computational problem with very specific features, they would also impact the course of developments of the quantum hardware technology. So that's the hope. So because this crowd is not quite quantum field theorists, but quantum computing experts, I'll keep the theory development part very short and very quick, and I talk mostly about algorithmic and implementation and benchmarking for this program to just sort of make this point clear what I mean by this sort of co-development of this program with also the hardware and algorithm expertise. So what do I mean by theory development? This is a long equation that I have here. Just want to show you that the Hamiltonians we are talking about are complicated. I don't expect you to know exactly what each ingredient of this equation is. All I want to say is that the Hamiltonian that we are interested in simulating from the perspective of simulating a standard model eventually would be the Hamiltonian of an abelian or non-abelian gauge field theory, right? So this is a quantum field theory that is also having some sort of global or local gauge symmetries. So in the form of a lattice-sized Hamiltonian, Koget and Susskind told us many, many years ago or decades ago how to write down this Hamiltonian. And the Hamiltonian has several terms. And each of these terms come with their own interesting features. In particular, in higher dimensions than just one, this last term would become important. If you are in 2 dimensions or 3 dimensions, which is exactly the physics that we want to simulate, this last term actually is very complicated. This is called a magnetic field interaction. And it requires higher body interactions than just 2 body. So in this case, either 4 body or 8 body, depending on your quantum hardware. But the important thing I want to make comment about this Hamiltonian is that you have the fermions, which are the psi fields in here. So we have the fermions just like in quantum chemistry problems. But we also have the bosons, as I said. And these bosons are bosonic fields. They're not just like a single oscillator. They are fields. And because of that, so these U's and L and R, these are bosonic fields. And these are exactly those gauge fields that we are talking about. And simply because they are bosonic fields, they have infinite dimensional Hilbert space, which is a problem for the simulator. We have to cut off the excitations of these fields such that we can contain them in a quantum computer or quantum simulator and be able to simulate them. Of course, then the question is that if you just cut them off too quickly, right? If this cutoff is too small, then maybe you don't get the physics right. Maybe you need, and that's a factor in understanding the resource requirements for reaching a particular precision in this program. If you need a very, very large cutoff on this excitation of the bosons, then maybe even in the far term, we would be far away from getting the answer that we want out of this program. So it's an important question to explore. And already by classical methods, whether exact diagonalization or tensor network methods for small systems, you can start to answer this kind of question with a hope that you gain some insight on what the right cutoff value on the bosonic fields is, to be able to then go and map it to the finite number of qubits that you have in your architecture. And in fact, we've looked into this problem extensively for this non-abelian gauge theory. The detail doesn't matter. In this case, it's an SU2 gauge theory coupled to fermionic matter, but only in one dimension. And what we see is, of course, for lowest state in the theory, say the ground state, you can already describe the ground state energy. So this is the difference going to zero with very high precision already with a small cutoffs. So these are for different colors for different states. The first one, just randomly the 21st one, and this is the highest state, 283rd, and there's a small lattice for different coupling constant as a function of the cutoff on these excitations. And as you see, fortunately, things are converging exponentially to the right value. But as you go to the higher and higher states in the theory, this convergence is very slow. So you need higher and higher cutoffs to be able to describe the ground state with certain precision. And for dynamical quantities, this is even more challenging, because if you're interested in the long time dynamical simulations, then the cutoff value should be large. As you can see, for different times for the simulation of some particular dynamical quantity in this theory, that the detail of which doesn't matter, if the time is large, then even for the first few lambdas, you're not even in that exponential scaling regime that would give you the right answer eventually. So you can already see that as we are going to do the simulations for long times, we are also needing to increase the resource requirements for the simulations on the hardware side. So that's what I mean by theoretical development. The other aspect which is very important is what I didn't tell you about this Hamiltonian was that the Hamiltonian itself is invariant under gauge transformations, and in this case, local gauge transformations. And the generator of this gauge transformation is called the Gauss's law operator. Again, you don't have to worry about this formula here. It looks complicated. All the Gauss's law would tell you is that if you just naively build the Hilbert space of this Hamiltonian, it's very large and most of it is just redundant and unphysical. Only a very small sector of your Hilbert space is actually physical. That's the sector that satisfies the Gauss's law, or this gauge symmetry is sort of an eigenstates of those gauge symmetry transformations. And this is called the Gauss's law sector, or the physical sector. And you can understand it from sort of electrodynamics. If you remember the Gauss's law, that's exactly the same thing. The divergence of the electric field should be balanced by the charges or the matter charges at each point. It's going to be very complicated for non-abelian gauge symmetries, like the theory of strong interactions that we're interested in, because then with non-abelian symmetries, things are more nonlinear and more difficult to solve. And in fact, so this is that picture that I was talking about, kind of schematically, the Hilbert space is so vast, so large, but only a very small sector of it, which is already exponentially large itself in the size of the system, but it's a very small portion of the full Hilbert space. So you don't want to really waste resources in your quantum simulation on the sectors that you have no interest in, right? So again, from a theoretical perspective, that's where the theorists come in and say, all right, let me fix this problem for you to give you a suitable formulation that already puts you in the relevant sector of the theory, so you don't waste your resources on the irrelevant sector. So that's why these kind of theory developments in this program is also very important. And this is sort of an example that we worked out again in a non-abelian gauge theory, and we showed that in fact, by hundreds of orders of magnitude, the size of the full Hilbert space is larger than the size of the Hilbert space that we are interested in. This is physical. So it really, really is important to kind of come up with ways to actually stay here, start here, stay here, and end here. Otherwise, you're kind of spoiling the simulation into the unphysical sector. And there are ideas on that. I want to not go through them, to how to really, if you actually have this leakage to the unphysical sector, how to come back. But this is also very useful in the other context, right? If you're interested in a condensed matter problem or quantum chemistry problem, there are certain global or even local symmetries that you want to satisfy. And just simply because quantum simulation in a digital manner, for example, a Trotter expansion of the unitary time operator would break the symmetry already, even if you had a perfect hardware. Or if you had an imperfect hardware and gates and so on, that could break the symmetries and take you away from the physical sector. How do you mitigate that? That's a very important question. And there are already ideas out there. I refer you to this paper. I'm not going to tell you about it just to get to the main part of the talk. How to deal with this in a general problem with just sort of general symmetries, or in the context of these gauge theory simulations, how to deal with it and really suppress this leakage to the unphysical sector of the theory. So these are really ideas that are becoming very, very hot, and it's a very active field of research at the moment, how to protect symmetries in a simulation. And again, more references if you're interested in that topic. I say a few more words and a stop for questions, and before I really start the main part of the talk. As I said, so let me skip this one actually. This is just to say that, again, we can be clever and come up with better constructions or formulations that already puts us in the physical sector of the theory and save us in terms of computational resources. And there are a lot of formulations out there, at least for abelian, non-abelian gauge theories, that are proposing sort of these more suitable constructions. And in fact, each of them comes with their own pros and cons. And the question is that really which one of these Hamiltonian formulations for gauge theories is the one that we have to stick to in the quantum simulation program that would really make our life easier and save us resources and so on. And the same with the scalar field theory, not just the gauge field theories. In quantum field theories in general, there are some ideas out there. And in fact, it kind of started this very excellent work of Jordan Lee Preskill on a scattering problem in quantum field theories, and kind of sort of exploded in all directions at the moment. And it's a very active field of research. In fact, if you're interested, this current week, we are having a workshop on this very particular topic. What are the theoretical strategies in the quantum simulation era for gauge field theories, so that we can actually be more wise and clever about quantum simulation of these theories once we have these devices. And in fact, let me also mention that in the FAR-QC seminar series, I think on April 21st, if I'm correct, you're going to hear from Nicholas Muller on quantum algorithms for a scalar field theory. So that other part of the picture that I was talking about, he's going to tell you about some recent developments on a scalar quantum field theory simulations and from an algorithmic perspective. All right. So I'll stop here and I'll see if there are questions. before I tell you also about the algorithmic and implementation and benchmark developments in this program.
I have one more quick one if no one else has one.
Sure.
So you mentioned this, the Hilbert space problem. This is, it sounds to me like an artifact of the construction, not necessarily, this isn't like where you mentioned cutting off the oscillator states. Those are physical systems that you just have to truncate because to put it on a digital computer. This sounds like something a little bit different there. That's actually just an unphysical artifact of the
yes,
construction.
absolutely.
Is that right?
Absolutely okay. Right. Exactly. You captured what I tried to say really with this slide by saying that this was the most naive way to go about it. So this very first slide that I had here, and I said this is one formulation of the Hamiltonian gauge theory that for decades people have taken as sort of the standard approach. And this is really important to mention that it's really started sort of the developments in this field. But then now realizing that this is not the most efficient way to go about this problem because it has these redundancies in the construction, people have started to ask the question of how else and can I do this better, right? Do this construction. And that's why we have all sorts of ideas and proposals now out there. But none of them, unfortunately, is perfect at the moment. And that's why we have this workshop to really go through them and understand the pros and cons of each of these constructs. In the end of the day, most of them, except maybe for one or two formulations, have this problem of having to deal with this bosonic excitations, right? The cutoff that you have to put to make the problem finite size. Good.
Thank you.
No problem. Other questions? All right, so if none, let me continue. So, of course, in this crowd, we all know what the quantum simulation means and what are the different approaches to the quantum simulation. For the sake of what I want to say for the rest of the talk, let's distinguish the analog and digital and something that is kind of in between. All right, so in an analog approach, you have a natural quantum system or a physical system has some sort of intrinsic interactions. And you can also engineer those interactions given the intrinsic interactions of the system and the environment. And then hopefully you can figure out how to make those interactions to look like the interactions in the desired theory that you're trying to simulate. And then once you start the experiment, basically it evolves the system with the exact unitary time operation that you're hoping to simulate. And that's the quantum simulation experiment. But of course, in a digital approach, we are only given a finite set of gates or universal standard set of gates. And therefore, we digitize the simulation in the most common way. You can do a Trotter decomposition of the unitary time operation, assuming that you have this local or k-local Hamiltonians, so you can separate them. And then you can implement each of these terms separately at the cost of introducing this digitization error or Trotter error or some other type of errors. No matter what you do, once you digitize, you incur this kind of errors, of course. So this is sort of the digital approach. And something in between would be, well, maybe you have more than just the qubits. Maybe you have more types of degrees of freedom you can take advantage of, but also maybe you can come up with more sets of gates, not just those finite universal set of gates, given the intrinsic interactions in your system. So you're really combining the benefits of each of those approaches in one approach by saying that, well, I can't really simulate or engineer the exact Hamiltonian I want in this form. It would be very difficult. My hardware would not allow me to do that, given its intrinsic properties. But I can do some sort of digitization still. But why not also using the extended set of gates and also degrees of freedom to enable the simulator even further. At least in near term, when we don't have enough qubits and good enough gates to do everything digital, right? That would be the eventual goal. So in order to demonstrate this, let me pick a problem and also a platform, okay, to just give you the very explicit, concrete examples of what I mean in this, comparing these approaches, at least for lattice gauge theory program. The platform that I'm gonna pick are the trapped ion systems. And the problem that I'm gonna pick is a one-dimensional lattice gauge theory called Schrödinger model. You can think about this as an electrodynamics in one dimension. And of course, eventually we're interested in electrodynamics in 3 dimensions and in quantum chromodynamics in 3 dimensions, which is really much harder. But let's just start from this simpler example, which is still too challenging for the current technologies and hardware. All right, so that's the thing I wanna focus on. And let me repeat again, in the digital scenario, the set of the gates that are available to us are either single qubit gates. So in this language, these are just single spin rotations, or 2 spin gates or 2 qubit entangling gates. So in the language of the trapped ion systems, of course, these are Molmer-Sorensen type operations. But the thing about the Molmer-Sorensen type operation is the fact that there are phonons in the system that are the common normal modes of the motions of the ions in the chain. But you don't directly use these phonons as degrees of freedom to look at their dynamics and so on. You use them indirectly, sort of in a virtual way, to induce interactions between the various ions on the chain. And that's why you can make these entangling gates. So the phonons are very important in the process, but they are not explicitly appearing in the quantum simulation. So now what we're thinking about is an analog digital setting in which you still have your single qubit and 2 qubit gates, but you also extend your gate set to include the spin phonon gate as well as maybe the phonon-phonon gates. So the types could be there, the normal phonon, phonons that are coupled to the spin, but you can also make them even local phonons that are coupled to the spin. So these have different properties, of course, and they can come useful for different problems. And with this kind of a standing wave gates, and I'm not going to go through the technicalities of how to make these things, you can achieve also phonon-phonon entangling gates, at least locally. So let's say that we have this gate set. And in fact, this is doable if you ask the experimentalist colleagues. And again, in the analog setting, there is no gates. You just make sure that you tune your system in such a way that you have the right Hamiltonian to start with. Okay, so these are the 3 approaches. And now I'm going to go through this example of the Schrödinger model, this one-dimensional lattice gauge theory that I was talking about, and tell you that for this particular gauge theory, what can be done within these different approaches. All right, so what is the Hamiltonian? Once you map the fermions to the spins, then it's basically just the spin sigma z operations, easy. So this is the mass term. The next term is going to be 2 sigma operations, but now you have these bosonic gauge fields that are sitting in between, expressed in this form of e to the I theta n. And then you have the electric field term. Again, these are bosonic excitations. They're discrete excitations by integer. And this is sort of the electric field term, right? So you see already this is more complicated than what you expect from a purely spin Hamiltonian, right? Because it's bosonic fermionic, and it's has this sort of also the nearest neighbor interactions with the bosons. One thing that you can do, which is a trick that you can always do in one-dimensional theories, but not in higher dimensions, is to eliminate the gauge degrees of freedom, which are the ones that are making things a bit difficult, using this Gauss's law, as well as some gauge transformation. So just believe me that you can do this, and if you're interested, just do it. Just use these equations here, and then show that this Hamiltonian actually becomes a purely spin Hamiltonian in one dimension. It's an interesting Hamiltonian because now it has sigma z, it has sigma plus sigma minus nearest neighbor interactions, but again, it has sigma z type interactions that are all to all. So this is a non-local long range interaction, which is really the Coulomb interactions in 1D. Okay, just kind of the linear interaction. And so this is expected. Of course, we cannot always do this and end up with a spin Hamiltonian like this if you are in higher dimension, but at least for the Schringer model, we have this choice. We can either do the simulation of this theory directly or go to this equivalent formulation if your boundary conditions are open in 1 dimension. So that's really the model. That's all I want to say about the model. You don't really have to know much about this. The thing is that this model actually produces a lot of interesting features that we see in some complicated theories like QCD. And in fact, it has features like chiral symmetry breaking, if you know what that is, and creations of pairs of electron and positrons, and a non-trivial theta vacuum and things like that. So this theory is very non-trivial, despite the fact that it's 1-dimensional and so on. So it has very rich physics. So it would be nice to actually explore it with a quantum simulator first. So this is how the mapping would go. So on the top panel, I have the sites where the fermions are sitting, these psi operations, and there are links that are connecting the fermionic sites. And on the links, there are sitting electric fields or the gauge links, which are the conjugate variables to each other. So the links are bosonic, the sites are fermionics. And what we can do in a digital approach, and when there is no gauge degrees of freedom, let's say that I'm going to this purely spin formulation of the theory. So everything is now a spin. We get rid of these E's and U's using the tricks that I just told you about. And therefore now everything is mapped to a set of qubits, these sigma j operators or the ions. Then you have your lasers tuned and you do operations on this, easy, right? And you use the normal modes of motions to perform the 2-ion entangling gates, and then you use the internal states of the ions to encode the dynamic of the fermions or the spins in this case. Easy, okay? And this is really the very, so this is kind of the quantum circuit for what I just showed you. These are nearest neighbor entangling gates for XX and YY type interactions. But you also have non-nearest neighbor, all-to-all kind of interactions that are of the type of sigma z, and then you have the single qubit interactions. That's really is the simplest circuit that you can come up with for this problem, which is nice. And in fact, the very first implementation of such the dynamic of the lattice Schringer model on a quantum simulator was already in 2016. It created a lot of excitement in this program because although it was a very small system, a 4-qubit simulation in the trapped ion system in Innsbruck, it actually showed the community that, yeah, maybe someday we can do real-time dynamics of gauge theories using this quantum hardware. Might be a long time in the future, but this is really the starting point. We can actually create pairs of electrons and positrons as a function of time and track their dynamic starting from some trivial vacuum, which is quite exciting. Again, very small problem, but the first step. So that's what they did. We are also extending this dynamics to much longer times. In fact, the systems in Maryland have quite progressed compared to what it was in 2016 in Innsbruck. And in fact, beyond the first few points that the Innsbruck group have done, you're able to really achieve a much longer evolution time and see very interesting physics. So this is some work in progress in Norbert Lincoln Lab at the University of Maryland. So what about the analog approach, right? I mean, the digital, fine, it was a simple circuit. What about the analog approach? For the analog approach, if you are looking at that purely a spin system, forget about the gauge links and so on. Let's imagine that I have already eliminated them and I have this purely spin Hamiltonian, which is an Heisenberg Hamiltonian with all-to-all interactions in the end of the day. Can I in an analog way simulate the system, it sounds very complicated, right? So in fact, the technology isn't there yet, but it's not too far-fetched. And in fact, there is an experiment now being built by our collaborator, Guido Pagano, to sort of impose, bring to life this experimental proposals that we had in this paper of how to do a purely analog simulation of the Schwinger model. And in this case, it turned out that not only you have one set, you need one set of addressing beams, you need 3 sets of addressing beams that are being tuned in a very particular way, given the direction and intensities and the detuning the frequencies, and that would enable, without cross-talking, the simulation of these Heisenberg all-to-all interactions. If you're interested, you should really look at the details of this paper that we worked out. And in fact, we give very concrete, exact experimental proposal for what the parameters of the experiment should be to, for example, exactly optimize and simulate with very high accuracy, for example, the nearest neighbor, or even this particular long range sigma z interactions in experiment. So the proposal is there, and hopefully at some point we will have the experiment to demonstrate a fully analog simulation of a gauge theory in this fashion. All right, so now what about digital? I mean, I already told you about digital, but kind of by, it's not cheating, but in 1D, we can do this. In higher dimensional, we cannot really replace these bosons or gauge links. So we have to learn to deal with them anyway. So let's say that I have in this one-dimensional Schwinger model, but I don't replace or eliminate the gauge links. I keep them. I want to figure out how to deal with them. What is the corresponding algorithm for simulating dynamic in the system in a digital way? So of course, what that means is that now your interactions, your system size is going to be much larger in terms of the hardware, because not only you have to map your fermions, you have to also map your gauge bosons. You have to cap the excitations of the bosons to some finite number, of course, as we said. The higher this cutoff, the more qubits you need to put in between these fermionic qubits. But in the end of the day, you have to have of the order of logarithm of that cutoff on the bosonic excitations for the qubits to encode these gauge links. So already in terms of resource requirements, this is quite large, right? The other question is that, well, can we actually have efficiently simulate the interactions now? Because not only the gauged bosons are interacting through the electric field term, they're also interacting with the fermions, but also there's the mass term, which is easy. Okay, so the question is that, is it efficiently simulable? And that's the question so this is another work based on this digital approach that use some tricks using the hybrid classical quantum approach to simplify this problem. So they still have the gauge fields and everything, but they use the classical pre-processing to reduce the size of the Hilbert space that or the Hamiltonian that they're interested in, so that then make it amenable to simulations for the current hardware. And in particular, for the same size of the problem that the Innsbruck group has done, you can, with the 4 qubits, you can reduce this problem with the classical pre-processing to just 2 qubits. And because it's a 2 qubit system now, you can do a very long simulation time. So this is a very nice work that came out of the collaboration between University of Washington and Oak Ridge on another DOE collaboration that produced this nice result. And that's one approach, but you might ask whether this is scalable, because eventually for larger systems, the classical pre-processing can be very costly and might not be doable, right? So we don't want to go through this approach. How if we actually go through just writing the quantum algorithm for the actual size theory? And this is another very nice work that has been done last year, again, Pavel Gauss at the time at Oak Ridge, but currently in Amazon, and collaborators, including Alex Shaw, Jesse Stryker, and Ethan Wiebe, that they came up with efficient algorithms for simulating the electric field interactions, the gauge matter interactions, and the mass term in the Schwinger model. This is kind of the circuit, and now you see the complexity of the circuit, and this is not the entire thing, it's just like one trotter step for certain blocks. And as you can see, it's already very complicated, lots of entangling gates, including all-to-all gates. But you can understand why that's the case, because again, you have the gauge link that is being sort of encoded into multiple qubits. The multiple qubits should talk to each other through the interactions of the electric field term, but also to the qubits represented by the fermions. So there's going to be a lot of entangling gates. So a near-term cost is going to be huge. And in fact, this is one of the few papers out there that actually has worked this out precisely for gauge theory. I think at the moment, the only one. And you can see that the requirements are of the order of 10,000, 100,000 C naughts to reach a given accuracy. So the requirements of this program are really huge, even for the simplest problem that we can take, which is the lattice Schwinger model, right? And really the very last thing that I want to say is about this analog digital approach that we're developing with the collaborators at the UMD, but also Guido Pagano at Rice University. Hopefully this would be out very soon. And the idea is the following. We are going to have a digitized operation, but we are going to use a more extensive set of degrees of freedom in the gates. And in this case, the degrees of freedom are both the normal and the local excitations of the motions. You can ask me later how people would come up with ways to actually have the local modes of motions in this kind of long chains of the ions. That's another interesting topic. But in any case, this is doable. And once you do this, now you can have that extended set of gates that I was talking about. And then as a result, the circuit for the dynamics of the Schwinger model becomes quite simple. Once you have this extended set of gates, you can represent the interactions of the fermions and gauge links by just this block. And you can represent the interactions of the electric field terms just by these standing wave gates, which is nice. What this means is that not only you don't have to represent the gauge links now in terms of the qubits, because they're naturally represented as the phonons in the system. So you don't introduce any extra ions in the chain. And in terms of scalability, that's very beneficial. But also, the gates would enable you to reduce the number of entangling spin-to-spin gates that you require in the fully digital implementation, which is great. So in terms of sort of the requirements for the spin-to-spin entangling gates, this is sort of what you gain in the analog digital approach compared to the fully digital approach, which these numbers could be quite large, right? So it already tells you that, yes, maybe near term, it's a good idea to think about this sort of hybrid approaches, analog digital. Of course, to understand whether it's actually beneficial, we have to do the experiment. And in fact, Norbert is very keen to try this because they have very interesting results on controlling the phonon dynamics. So we're hoping that we can actually run the circuits and see whether they are actually better in terms of performance currently compared to the fully digital simulations that we're performing. Let me skip this. And this is what I said about Norbert's experiment. If you the thing that got me very excited and I started to think about it and discuss this with Norbert and my colleagues is this paper that came out of Monroe Linke Group, where they look at the dynamics of the phonons themselves. They show that the experimental control over phonon degrees of freedom is possible, at least for the small systems, right? I don't know about the scalability or things like that, but this is really the start. And maybe it tells us that we can and we should start thinking about simulations that take advantage of phononic degrees of freedom as well. Let me skip this variational part. if you're interested in the second part of my talk, we have another workshop in this incubator for quantum simulation in University of Washington. It's going to be virtual, and it's going to be in May, and we are going to continue discussions of simulation of lattice gauge theories, but this time from the perspective of implementation strategies. So if you're interested, please tune in and get in touch. And I didn't cover a lot of excitements on the cold atom community of quantum simulation, because I wanted to kind of stay closer to the digital quantum computing community in this talk. But of course, there's been a lot of interesting and good progress in the cold atom quantum simulation community for lattice gauge theory program as well. And this is really the final word that I want to say. That really, I think we're just at the end of the beginning of the lattice gauge theory quantum simulation program. I think that the next serious phases are just starting now, but we need a lot of creativity, investment, not only in terms of money, but also in terms of people and ideas and sort of the commitment to this kind of problems. And we also need a lot of theory, algorithm, and experiment collaborations. That's very important in this co-development process. And I hope that I convince you that that's the case by going through these examples that I mentioned. And I think a lot of patience, because we're not quite there, but hopefully we will get there someday soon. Many thanks to my collaborators in this quantum simulation program. As you can see, it's very interdisciplinary. Not only we have very talented people in nuclear physics program, but also from the QIS and computer science community at the UMD, also in the AMO community, both experiment and theory, mostly at the UMD, but we also have great collaborators at other institutions now. So thanks very much.
That was very nice talk. Thank you very much. A lot of really interesting things. I know we're a little bit past our time here, but I'll leave the floor open if there's any really quick questions. And if not, folks, obviously, I think can contact you directly through email if there's any other questions. Any short ones from the audience? Okay, we'll leave it to virtual questions later on. This is, again, very fascinating. Thank you very much.
Thanks very much for inviting me.
Take care, everyone. Yes, thank you. Bye-bye all.